In this video, you will learn about the squeeze theorem, which some people call the sandwich theorem. What the squeeze theorem says is that if you have three functions, f, g, and h, and g of x is between f of x and h of x when x is near some value called alpha, and the limit of both f of x and h of x as x approaches alpha equals some value called L, then the limit of g of x as x approaches alpha will also equal L. If you look at the diagram on the left, you'll see that green function, g of x, is sandwiched or squeezed between h of x and f of x when you're at the x value alpha, and that all three of them have the same limit. We're going to use some algebra and geometry to prove that the limit as theta approaches 0 of sine theta over theta equals 1 using the squeeze theorem. So first off, we're going to start with this diagram. I've got a circle O that has a radius of 1, and so you can see the point on the right at T, which has coordinates 1, 0. We also have a line segment, PT, that is tangent to circle O at point T, and QR is perpendicular to segment OT. I'm going to walk you through this. We're going to find some areas. So we're going to start by finding the area of triangle TQO. I've outlined that in blue in the figure. Well, we know the area of a triangle is 1/2 the base times the height. The base of this triangle is segment OT, which we know has length 1. The height is QR, which we'll find in a second. And then, of course, we have the 1/2. So we're looking at 1/2 times 1 times the height of QR. Now, QR is a line segment, and alpha, the angle on the left, will help us find its length because QR is opposite to alpha, and the hypotenuse OQ is equal to 1 because that is the radius of this circle. So the area of that blue triangle, triangle TQO, is the sine of theta over 2. All right, so let's move on. Now what I'd like to do is find the area of sector OTQ. I've shaded that in blue so you can see it. Now remember, a sector of a circle is just a piece of a circle, and its area is some portion of the area of the entire circle. And that ratio of theta over 2 pi will tell us the portion of the circle we need. So remember, the radius is 1. Theta over 2 pi times the area of the circle, which is pi r squared. And remember, because the radius is 1, r squared equals 1, I end up with theta times pi over 2 pi. The pi's cancel, and the area of that sector is just theta over 2. All right, we need one final area, and that's going to be of triangle OTP, which I just outlined in purple for you. Again, 1/2 base times height. The base has length 1. The height is whatever TP is, and then I need the 1/2. So I've got 1/2 times 1 times PT. PT is opposite angle theta, and the adjacent to angle theta is segment OT, which has length 1. So that means I've got the tangent of theta equals PT, and if you work that out, you end up with the area of triangle OTP is tangent of theta over 2. And here's one kind of interesting fact. Notice that PT is the tangent of theta, and it's also literally the tangent line segment. That's not a coincidence. That's where the name comes from. Okay, so moving on. If you look at the figure, you can see that triangle OTQ, that's the first one we found the area of, has an area that's less than the sector, because there's like that little tiny piece on the right that's additional in OTQ, the sector. And then that's all smaller than the area of triangle OTP, the one that has the tangent line segment. And so what that means is sine of theta over 2 has to be less than theta over 2, which has to be less than the tangent of theta over 2. And if you just multiply all the way across by 2, that means sine of theta is less than theta, which is less than tangent of theta. All right, you may not see where this relates to the squeeze theorem yet, but you will soon. So moving, I just copied over what we've got so far onto this slide. So we know that 0 has to be less than theta because we have a triangle in the figure. So it's safe for us to divide by the sine of theta. If I do that, I get this. And sine of theta over sine of theta is just 1. And then the middle section stays what it is. Tangent of theta over sine of theta is just 1 over cosine theta. I'll give you a moment to think about that. All right, so what I would like to do is get sine of theta over theta so I match the thing I'm trying to prove. So I'm going to take the reciprocals. But when you take the reciprocals of fractions, the inequalities reverse. So think about it. If 1 is less than 2, and I take the reciprocals of 1 and 2, I get 1 and 1/2. 1/2's greater than 2, than 1/2. I have to flip the sign. And so I end up with this. And here we see the sine of theta over theta, which I wanted because I'm trying to prove something about it. And in fact, the thing I'm trying to prove involves limits. So let's take a look at the limits. The limit of 1 as theta approaches anything is equal to 1 because 1 is a constant. And if I want to find the limit as theta approaches 0 for cosine of theta, I need to look to the approach from the right, approach from the left, and also the value of the function to see if we're continuous there. So if I approach theta from the positive, 0 from the positive side, I'm going to get a cosine of theta that equals 1. And if I approach 0 from the negative side, I'm going to get a cosine value of theta that equals 1 again. I also know that f of 0, if my function is cosine of x, is going to be cosine of 0, and that equals 1. So what I have is my function approaches 1 if I approach 0 from the left, from the right, and also the function itself equals 1 at 0, and therefore the limit as theta approaches 0 for cosine of theta equals 1. Now, by the squeeze theorem, that means that as theta approaches 0, the sine of theta over theta's limit is 1. And note that this function, sine of theta over theta, is only defined when theta is not equal to 0. Otherwise, we'd have a 0 in the denominator. So at that point, we have a removable discontinuity. All right, so how is this useful to us? This function, sine of theta over theta, having a limit of as x approaches 0 of 1 is really useful when we want to find limits of other things. So look at this sine of 4x over x. It's not exactly in the form I want it, but I can do a little bit of algebra and it's going to be very easy to work with. So the limit, if I multiply by 1, 4 over 4, I can rewrite it like this. Now I've got 4 times the limit as x approaches 0 of sine of 4x over 4x. Well, sine of something over that something equals 1 as that something approaches 0. And if x approaches 0, 4x will also approach 0. We just proved that the limit as theta approaches 0 of sine of theta over theta equals 1. And so I know this part of what I've got here equals 1. And I just have 4 times 1 equals 4. So that is the limit as x approaches 0 for the function sine of 4x over x. Let's look at another example. I have sine of 2x over sine of 3x, and I'm interested in the limit as x approaches 0. If I can get sine of 2x over 2x, I'm happy because I'll know the limit of that. I also can get 3x over sine of 3x, and because that's the reciprocal of sine of 3x over 3x, I can use the same squeeze theorem that I did before. So let's see how that works. If I multiply by 2x over 3x, I can get what I want. And remember, the limit of the products is equal to the product of the limits. That was one of the first rules we looked at before vacation when we started talking about limits. So I can reorganize this. The 2x over the 2x there, I'm just multiplying by 1, and then the 3x is same thing. So let's look at the limits of each piece. This part here, the x's will cancel, and you end up with a limit as x approaches 0 of 2/3. This part here, by the squeeze or sandwich theorem, equals 1. And this part here, because I know that the sandwich theorem makes sine of theta over theta equal 1, that limit, the reciprocal will as well. And so I end up with a limit as x approaches 0 of sine of 2x over sine of 3x is just 2/3. All right, you try this one. You want to find the limit as x approaches 0 for sine of 3x over x. All right, so I hope that what you did is you multiplied the sine of 3x over x by 3 over 3, which is just 1. If you rearranged it, you got what you see here. And that means you have a limit for sine of 3x over x as x approaches 0 of 3. All right, here's another one. Find the limit as x approaches 0 of sine of 5x over 3x. All right, well, I hope what you did is you noticed that you needed to multiply by 5/3 in the denominator to get 5x down there. And in order to multiply the function by something that won't change its value, you had to multiply by 5/3 over 5/3. If you did, you got something that looks like this, and that has a limit of 5/3. All right, here's another one. Now, tangent is sine of something over cosine of something. Use that to help you find this one. All right, so I hope what you did is you realized that tangent of 3x is just sine of 3x over cosine of 3x. You've already got the 3x in the denominator that you need to get sine of 3x over 3x. And the 1 over cosine 3x, you actually can find the limit of without doing anything. All right, so the sine of 3x over 3x, that limit as x approaches 0 is 1. Now let's look at the cosine. If you put a 0 in for x, you're just being asked what the cosine of 0 is, and that's 1. So 1 times 1 is 1. All right, another one to try. Now for this one, you've got sine squared of 5x over x squared, so you can split it apart. If you multiply by 25 over 25, you'll be able to get the 5x that you need in the denominator for each of these two things that are being multiplied. And if I split that up, well, the limit as x approaches 0 of 25 is just 25. And the other two, by the squeeze or sandwich theorem, are both equal to 1. And so you end up with a limit of 25. Next one. All right, now this one you can split apart as well because the sum of the limits is the limit of the sums. So x over 3x can be split from sine of 2x over 3x. Then you're going to do a little bit of multiplying. The 1 over 3, because the x's will cancel in that first part, and then you're multiplying by 2 over 2, and you're going to get 2 times sine of 2x over 2x, and you've got the 3 in the denominator as well. And that's going to be 1/3 times 2/3 times 1. 1/3 plus 2/3 times 1, which equals 1. All right, so that's it for the presentation. Now you're going to have an opportunity to do a little bit of practice with what we've been doing so far this week. So please sign on to Delta Math and do the assignment called Continuity and Discontinuity Practice. And I will see you tomorrow.